we'll be able to send you the link afterwards. We don't guarantee that the recording actually will be will be for the entire duration, but we're trying our best with the technology here. If you have any problems with sound, please let me know by messenger, and I can send you the instructions for the dial-in. And if you dial in, you will be able to participate in the conference directly as well and ask questions to the speaker. Otherwise, on the computer, you can only listen. If you have questions, you can send them in this messenger window by text to me, and I'll relay to the speaker. So if you have any other technical difficulties during the presentation, please send me a text message, and we'll try to address it, work it out as the presentation is going on. So I think that's about it for the system check for the announcements. And just Kevin Keating here came from, as I mentioned, Yale University. He has a Bachelor of Science degree in computer science from Tufts University, which he obtained in 2004. Afterwards, he moved to Pyle lab at Yale University when he obtained his PhD in December of 2010. And the focus of his work was mostly semi-automated model building for RNA. And initially, he developed a number of methods for just automatic placement of bases and phosphates, and then he went on to develop the plugin that he will be talking about today, that is now integrated with the application, within the application Coot. And I encourage you to go and take a look at some of his publications. He has a number of them that were recently published in PNAS and other journals, and talk about the early stages of this method development, as well as another publication that he will mention today he's working on right now, actually about how to use the plugin, will be published in the near future as well. So without further introduction, just give it to you, Kevin. And as I said, if people have any questions, I'll relay it to you during the presentation.
Sounds good. Thank you, Piotr. And thank you, everybody who's here and listening in. So we've done the system check. So as Piotr mentioned, I'm going to be talking about RCrane. It's a Coot plugin for building RNA models into electron density. Before doing the demo, I just wanted to do a couple of slides showing you how RCrane works to give people some idea of what's going on behind the scenes with the plugin, hopefully to help people use it better and figure out what it's doing. So I'm sure most of you listening know RNA crystallography tends to be done at fairly low resolutions. This is just a plot of existing RNA crystal structures. You see a lot of them are done in sort of the 2.5 to 3.5 angstrom range, where if you're lucky, you're looking at maps that look like these. These are actually both model phase, so this is better than you're ever really going to get from an experimental phase map. And you can see from even these model phase maps, the only things you can really make out all that well in these maps are the phosphate locations and the base. The phosphates are nice and electron dense. They show up very well. The bases are large and rigid and planar, and they're the things sticking out of the density for the backbone. So placing phosphates and bases isn't too difficult, but getting precise positions for really anything else is incredibly difficult, very time-consuming, and usually not terribly accurate. You know, there's placing some of these sugar atoms. You can see sort of generally where the sugar goes, but trying to place the sugar itself precisely is almost impossible when you're just staring at the density. RNA model building historically hasn't had very many good tools for model building, or really good ways to go about doing it. A lot of it started out of you sort of stare at the density that's not all that specific, and you try to cram in nucleotides, or you try to cram in stretches of nucleotides with a lot of guesswork, as I mentioned before, very time-consuming and fairly inaccurate. So with RCrane, what I've tried to do is add an extra step into the model building process, where you'd have a human being go from the density map, and with the help of the plugin, do this basic low-level trace of the backbone. So tracing just phosphates and bases. So as I said before, these are the things that are at least possible to make out with an electron density. And then from this trace, the plugin can calculate out very accurately and very quickly coordinates for all of the backbone atoms. So the way that this works is it uses 3 different means of analyzing RNA structure. One of those is the backbone conformers, and one of those is the pseudotorsions, and the base phosphate perpendicular distance. And so I just wanted to give sort of a brief introduction of what these 3 things are, since they're very key to the way that the plugin works. So the backbone conformers, you can think of these as the RNA equivalent of a protein side chain rotamer library. Here, instead of working with the side chains, you're looking at the backbone. So the consensus conformer library enumerates about 50 different preferred configurations for the RNA backbone. You can see I'm showing 6 of them here. They're all given 2-character names, typically a letter and a number. A number and a letter. So 1A, for example, is the helical conformer. So that means standard A-form RNA helix looks like this, and it can be called the 1A conformer. There's lots of other things. You can see 4N, 9A. There's a couple of things that I wanted to point out about these backbone conformers. The first is that they use the suite division of the backbone. So typically when you think of the RNA backbone, you think of nucleotides. The backbone conformers use suite, so it's going sugar to sugar with a phosphate in the middle. As I mentioned before, people typically think about nucleotides, where you're looking at phosphate to phosphate with a sugar in the middle. So you can think of suites as being sort of half offset from a nucleotide. So one suite contains the first half of one nucleotide with the second half of the previous nucleotide. The other important thing about the backbone conformers is that they're defined using approximate torsion values. They're not exact, so that means that if you had some structure that looked almost exactly like this, but there was one atom, a 100th of an angstrom out of the way, that still counts as the 4N conformer. It's the same way that the protein side chain rotamer libraries work. They're all approximate values. So for one suite, you get approximate values for delta, epsilon, zeta, alpha, beta, gamma, and the next delta torsion. And you'll see that there's 2 delta torsions per suite. The main important thing of that is that 2 adjacent suites overlap in their central in their central sugar. So that means here's one suite. This sugar is also contained in the next suite. So the next suite starts here and contains the second half of this nucleotide with the first half of the next nucleotide. One of the other means of analyzing the RNA backbone that this plugin uses is the RNA pseudotorsions. These are things that we've been using in the Pyle lab for probably almost 15 years now. The idea behind the pseudotorsions is you simplify the RNA backbone down. So I'm simplifying it down by looking at just phosphate and C1' atoms. So using these atoms, you can define virtual bonds. I'm showing them here in red. And you can get 2 pseudotorsions, so eta and theta. And if you take these two pseudotorsions, you can do the same things with them that you can do with, say, a protein Ramachandran plot. You have 2 numbers that represent each nucleotide. So you can plot them in 2 dimensions, and you can look at this plot, and it can tell you things about your structure. So in the past, we've used this a lot to analyze existing crystal structures. Here, obviously, I'm using it to build new crystal structures, but just wanted to give you some idea of where this means of analysis came from. The other thing, I mentioned the base phosphate perpendicular distance, and that's basically a way of determining sugar pucker. So I mentioned before, if you're looking at RNA density, typical RNA density, trying to pick out the sugar pucker is really, really difficult and many times just absolutely impossible, especially when you're working with experimentally phased data. So in this map, you can see that the sugar should go somewhere in here, but trying to figure out exactly which atom is out of plane is nearly impossible. So with the base phosphate perpendicular distance, you can figure out sugar pucker through this very simple metric. You take the glycosidic bond, you extend it out infinitely in either direction. That's what this black line is for, just a line drawn through the glycosidic bond. And then you measure the distance from this black line to the 3' phosphate. So what you're, in the end, interested in is the distance of this yellow dotted line. And if you take a look at a data set of existing crystal structures, you can see that the data divides up very, very nicely. Anytime this base phosphate perpendicular distance, or p-perp for short, anytime this p-perp distance is longer than about 2.9 angstroms, you know you're working with a C3' endonucleotide. Anytime it's shorter than about 2.9 angstroms, you know you're working with a C2' endonucleotide. I should point out that this technique is the same thing that's used in molprobity. So if you feed an RNA structure into molprobity, and it tells you you have 11 sugar puckers that are questionable, it's using this same metric. And I can't take credit for this. This was developed in the Richardson lab, and as you can see from the plot, works very, very nicely. So if we jump back to the slide that I showed before, this figure in the middle here looks pretty much like the pseudotorsions that I was just talking about. This figure over here looks pretty much like the RNA backbone conformers. So the main trick with RCrane is it helps you place phosphates and bases and then uses the pseudotorsion information and the p-perp distance information to predict and build the appropriate conformer. So jump back. So the way that this prediction works is RCrane for every single suite. So let's say we're looking at this suite, it'll give you a list of guesses, which says the most likely conformer is 1A, and the second most likely conformer is 1C, and the third most likely conformer is 4A. So that gives me a really easy way to try to figure out, okay, how accurate are these predictions? I can take a data set of solved crystal structures where I know what the conformer should be, feed them all into RCrane, have it make guesses about the conformers using just phosphates and bases, and say, okay, how accurate was the first guess right? How accurate was the second guess right? How many times was the third guess right? And you can see that the first guess is almost always right, about 80 to 85% of the time. Usually when the first prediction isn't correct, it's the second or the third guess. You usually don't have to go any lower than that. So just as a very quick proof of concept to show you that this technique at least can work, I've rebuilt a couple of high-resolution crystal structures. So here the green is the previously published coordinates. The ball and stick is what RCrane was able to rebuild using just phosphates and bases, so that the ball and stick hasn't been minimized against the electron density. And you can see that this prediction methodology works very, very well. One caveat with this in the previous slide is I'm using published coordinates. So just to make sure that these published coordinates are going to be less accurate than you'd expect when you're first building into experimental density. So just to show you that this inaccuracy isn't going to affect the predictions, I reran all the predictions after randomizing the coordinates to sort of simulate error that you could expect from experimental phased density. And you can see you really don't lose much accuracy from base angle and base movement changes. So basically rotating the base within the plane or moving it around. As long as you're within about 2 angstroms, maybe 1.5 to 2 angstroms, you haven't lost much accuracy. With your phosphate coordinates, that does need to be a little bit more accurate, but as I mentioned before, phosphates are very electron dense, so trying to get them within an angstrom or an angstrom and a half of their correct location isn't a horribly daunting task. I should also point out, just to give some sense of scale for this plot, 2 adjacent nucleotides in an A-form helix are about 2.7 angstroms apart. So if you're working over in this area of the plot where you have 3 angstroms of error, you're probably building nucleotides past where the next nucleotide should be, and this really isn't an atomically interpretable map. And so with that, I just wanted to go into the demo and show how RCrane works, and you guys have some idea of the background and what it's doing. So here we have, this is 3.1 angstrom experimentally phased RNA density. We're fortunate here, the experimental phasing actually worked very, very well. But obviously, as you can see, especially if you're used to looking at protein maps, this is just incredibly low resolution. To give you an idea of what this is supposed to be, here's a structure that was eventually built into this map. But obviously, when you're starting out the building process, you're just going to be looking at this. So to use RCrane to trace density, to trace the structure, the first thing I would do is try to find something close to a phosphate, someplace where I want to start the trace. So let's say I've decided, okay, this looks like a phosphate, and then this would be the backbone, so here's another phosphate and more backbone. This would be a base, so I want to trace a nucleotide that goes from this phosphate to this base up to this phosphate. So again, first I'd move my screen center, that's this little pink dot that you can see, someplace close to where I want to start the phosphate. I go up to the RCrane menu in Coot and say I want to do a new trace. RCrane will look at phosphate coordinates, predict all the potential phosphate coordinates in the map, and then just try to select the one that's closest to where the screen center was. So that's why it's important to get the little pink dot near where you want to start the trace. So you can see right now RCrane is suggesting a phosphate coordinate right in the middle here. That sounds good to me, so I'm going to click accept. Now RCrane is going to try to trace the next nucleotide, and you can see it's done things a little bit backwards from what I was aiming for. For the first nucleotide, it doesn't have any directionality information to go on, so it doesn't really know that I want to be tracing up as opposed to tracing down. So it's traced something in the wrong direction for what I want it to go, but I can correct that. I'm just going to go over to the RCrane window and say next phosphate. So that's going to cause RCrane to try to give you a second guess for the next nucleotide. You can see now it's going in the right direction, but it's swapped the base and phosphate position. So I'm going to click next phosphate again. Okay, there we go. So now it's traced what I wanted to trace in. And you can see it's placed the phosphate, it's placed the base. That looks pretty good to me. So I'm going to click accept nucleotide. Now RCrane is going to try to build the next nucleotide, and now it has some direction information to go on, and knows it should be building in this general direction. So you can see it's placed the next nucleotide right about where I was talking about before. So we're going this way with the chain. So that looks pretty good to me. I can click accept that nucleotide. Now it's going to try to build in the next one. You can see the density has sort of gone around a corner here, but RCrane has managed to build the next base in correctly. So I could click accept nucleotide, but just to show you some other features that are part of RCrane, if I know the sequence that I'm building in, so if I know the portion of the molecule, I know I'm building in a GNRA tetraloop or some specific type of sequence, I can pick the appropriate base type from here. It'll change the base as I'm tracing. If you have other structure in the area, if you have some reason to believe that this base is syn instead of anti, you can click this button. It'll flip the base. You'll notice it's not just rotating chi 180 degrees. It tries to keep the base roughly in the same position of space. The idea being if the nucleotide is already in the density, you don't want to move it out. So this flip button will adjust it anti-syn. We're trying to keep it within the density. If for some reason you want to tweak the base position, you can click on this manually adjust button. It'll open up another window. You can start rotating things a little bit. This is really useful if you're tracing a helix, or if you know if you know via base stacking that you have some more information about the base plane. Sometimes you can tweak the base and get things a little more accurate. Again, that looks pretty good, so I'm going to click accept nucleotide. And this is basically the main component of the tracing section is just RCrane will attempt to build a base and you tell it yes or no. This looks pretty good to me. I know, since I know this molecule, this is a density for a base that's stacked. So this is about what I want to have built. So again, I'll click on accept nucleotide, trace a couple more nucleotides. That looks good. Click accept. Okay, so now we've got about 5 nucleotides traced. And I could keep going. You can see RCrane's managed to trace the next nucleotide, but just in the interest of time, I'm going to say, okay, that's all I want to trace right now. So I want to take this trace and build in the full backbone. Just going to reposition it so that you can see what's happening once it starts to do the coordinate calculation. And if I click on build backbone, so it's right below the accept nucleotide button, RCrane is going to start calculating out coordinates that match. First it will predict conformers, and then it's going to calculate out coordinates that match the predicted conformers and the predicted sugar pucker, and that match the base and phosphate positions that we just built in. I don't know how well this is coming through on the webcast, but you can see basically it looks like a standard Coot minimization. You can see atoms moving around. It's going to try to build one nucleotide at a time. If you're looking closely and if you have a good enough frame rate, you can see occasionally it's going to build a nucleotide and then all of a sudden flash and try to rebuild the same nucleotide. What's happening there is it's trying to build in that nucleotide with an anti-sugar. Then it'll try the same nucleotide with a syn sugar. And then if neither of those work, it'll try to build it in a high anti configuration, basically just making sure that the minimization doesn't get trapped in a local minima. So this minimization is going to take a little while since this laptop is rather old and somewhat slow. Excuse me. But you get the RCrane window will tell you your progress. And I should point out that during this minimization, the bases and the phosphates that we just traced in are allowed to move, but only slightly. So you may see things, especially bases, the base plane may get tweaked a little bit just to help the backbone fit into position. But nothing should go floating off, and certainly nothing should get pulled out of density. This hopefully should just take another 30 seconds while it does its minimizing. I can tell you at least on my desktop, which is significantly faster, this whole process is done in maybe 5 to 10 seconds.
So one question from the audience here: the minimization you're actually doing here on the screen, is it using the same type of calculation as Coot would use to regularize?
Yeah. So it uses the same minimizer that's built into Coot. The idea is basically the same as the regularizement, where I am paying attention to density, but very, very slightly. My weight on density is very, very slight, and I'm imposing the torsions from the predicted conformers is the main difference over just sort of doing a standard Coot real space refinement. Is I'm imposing fairly tight torsion constraints and also imposing very, very strict restraints to try to keep the sugars puckered appropriately. So I'm building in either a standard C3' or standard C2' endo sugar pucker, and to make sure that those don't get flattened or don't get distorted during the minimization. The sugar ring torsions are very, very tightly constrained.
And is it possible to change this weight? Is it something that could be tweaked by a user? Or
not right. Well, you can edit the source code itself, but right now there's no easy way to tweak those things. I've tried to set parameters that work that are fairly general. Let's see. The only time you can run into problems is if you're trying to build and there's really, really absolutely no density there. I've seen things get pulled a little bit out. But the only reason I was even able to start tracing something there was because I knew exactly what was supposed to be there, because it was going back to an experimental map where I had no density with a published structure, so I knew what was there. For the most part, I've tested a handful of maps, and the parameters seem to work fairly well. If anybody has trouble with them, they're certainly more than welcome to email me and let me know what's happening. I can try to fix it and try to play with weights and see if there's anything I can do to get things working.
And if this is right now partially built, and let's say you want to go and tweak one of the bases, can you easily rerun the refinement in Crane, or how?
So I can show you later how you'd go about re-rotamerizing. Right now, once it's built, there's no way to go back and at least directly change phosphate and base coordinates while it's building. You can go back later and fix things. What you can do is tweak the backbone conformers, which is, you can see the window that's popped up now. We'll let you do that. But at least right now, there's no simple way after it's built to go back and tweak those things. I can show you in a couple minutes some way to go back and tweak a couple things along those lines.
Great. There's also actually questions from the audience. There was another question, if you could at some point go back and repeat to show people how to place this first phosphate.
Sure, I can do that.
Okay.
Yeah, actually I was planning on doing that in a minute anyway for something else. So you can see right now I have the RCrane window. It looks different than it did during the tracing. So right now you can see all the suites that got built. So there's 4 suites that we built, 5 nucleotides, but because of that whole offset thing, we only built 4 suites. You can see all the conformers that got predicted and built. And for each suite, so right now we're focused on suite 2. That's what you can see right here. That's in the center of the screen. So that got built in as a 1A conformer was the first guess. And I mentioned before 1A is the helical conformer, so that's usually a pretty safe guess if that's anywhere on your prediction list. If for whatever reason you weren't happy with the way this nucleotide fit into density, you can pick an alternate conformer, click on that, and RCrane will repeat this minimization procedure, not for the entire structure, but just for the affected nucleotides, and it'll rebuild them. Excuse me. And so again, this will take a minute because this laptop is fairly slow. I should point out, since I mentioned before, suites overlap in their central sugar. So if at any point you pick a conformer that requires a sugar pucker change, RCrane will wind up rebuilding more than just these 2 nucleotides involved in this suite. It's going to adjust things to try to fix it so that the conformers work. Because obviously, if one suite ends with a C2' endo sugar pucker, the next suite has to begin with a C2' endo sugar pucker because it's referring to the same sugar. This will just take another 30 seconds while it does the minimization again. Yeah, and you can see right here the base has been pulled just a tiny bit while it's been doing the minimization, and there we go. So now we can look at the newly calculated suite. So this is now a 1L. That took a little while, so I don't really remember what the 1A looked like. once a conformer has been calculated, you can just jump back and forth between the two of them to compare them easily. So here 1A looks fine. I'll stick with that. You also notice that in this overview window, first off, I can jump to any suite I want by either using the next suite and previous suite buttons or just clicking on it in the overview window. You'll see that suite 5 is highlighted in yellow. So this is using the same stoplight coloring that you get, say, from refinement results in Coot, where things that are in white are sort of standard. Those are probably okay. Things that are in yellow, you probably want to at least take a quick look at. I don't have any here, but if I jump back over, to my slides for a second, you can see occasionally you'll get things in orange or red. Again, orange means that you probably need to pay more attention than yellow, and red means something probably funny is going on. You really should take a look at that nucleotide. There's two reasons you can get things colored. If I jump over to nucleotide 5, you can see one of the reasons is if my first and second conformer predictions have a similar score. So these scores, this entire column is going to add up to 1 for every single suite. You can see here we have a 0.25 and a 0.54. So they're not that close, but they are a little close. So that's an indication that maybe you want to take a closer look at this, this suite, and maybe try some of the alternate conformers. The other reason you may get something colored in is if coordinate calculation couldn't find a good set of coordinates that matched both the predicted conformer and the phosphate and base coordinates. So you may have some angles wrong in the backbone. You may have some bond lengths that are a little bit off. Basically, you should, if the structure looks chemically wrong, you can try an alternate conformer. That doesn't happen very often. It typically means that something went wrong in your tracing. You have either a base or a phosphate that's fairly far out, but that'll get flagged for you.
And this score itself, is it calculated based on the geometry or the density fit, or both?
Purely geometry.
Purely geometry.
Yeah, so it's calculated based on a mapping between the pseudotorsions and the backbone conformers, and based on the p-perp distance for how well it matches the sugar pucker.
And what's acceptable score?
Typically, the best scoring nucleotide, the best scoring conformer is your best bet to go with. In this case, the suite was flagged because there were things with similar scores. So usually if something's within, say, a factor of 2, it's at least worth checking it to see if maybe the 1C fits the density better. Here the density is not great, so it's going to be hard to tell. But usually your highest ranked conformer is your best bet, regardless of what the score is. These are always scaled so that they always add up to 1. So it's hard to get meaning from the absolute numeric value. It just basically tells you whether or not there was a close second guess, or I think if we jump back over to here, you see that the top score is 1, the second score is 0, so there's really no reason to try any alternate conformers here. Whereas here you might want to try things because it's close to an order, to a factor of 2 difference. Here again, I mentioned 1A was the helical conformer, so you might also want to take a look at the 1A conformer here. Just since that's helical, that's sort of a special case. Depending on how you measure it, about 70% of your structure should be 1A. So if there's something right in the middle of the helix and everything looks fairly helical, even when 1A is your second or third choice, it's worth at least taking a look and seeing how that fits the data. Okay, so when I'm done, I can just click the Done button. That'll close the RCrane window. And now if I head over to the Coot Display Manager, you can see I have RCrane molecule 2. I was tracing something before we started, but you can see that the molecule that we just traced is in Coot's Display Manager, and it's now a standard Coot molecule. You can do anything you want to it. You can save it, you can delete it, you can change the color or change the representation of it, or you can copy it into an existing molecule if you already have something traced. To go back and trace and show how to pick the central phosphate again, I can actually show 2 things while I'm doing that. So to build the first phosphate, the first thing you do is you drag your Coot screen center. So that's this little pink dot. Just drag it somewhere near where you think there's a phosphate. And then go up to the RCrane menu and select New Trace. You can trace in either direction. So this time, before we trace 5' to 3', here I can try to trace 3' to 5'. RCrane window will pop up, and by default, it's going to highlight its predicted phosphate that's closest to your screen center. So it's guessing this is what I meant. I put the little pink pointer over here. If that's not right, you can click on the next or previous buttons, and it's going to jump around. So all these green crosses are potential phosphate locations. I can use next and previous to move the orange square around. I can also click manually adjust if it didn't find the phosphate you were looking for. And then when I'm done, I just click accept. And now RCrane will use that phosphate location as the starting point for a nucleotide. I should also point again, so here I was trying to trace 3' to 5', so I was actually hoping that RCrane was going to go down, which it didn't. It went up instead. So again, use the next phosphate button until RCrane's trying to build in the correct nucleotide that I was looking for. I should also jump back here for a second. So here's where RCrane started off with. It's tracing in the wrong direction. You can see this base. It should be picking up base pairing with something over here. There's a helix running in this direction. So you can see right now this base is running parallel to the helical axis. That's because RCrane is trying to trace bases in that are standard anti-configuration, and right now we're trying to trace backwards. We're trying to trace the wrong direction. So a good way to tell that you're going in the wrong direction is your bases are going to be about 90 degrees off. So if I click the switch button, all of a sudden this base plane looks far more normal. It's picking up base pairing with the thing over here that I know it's supposed to be pairing with. Had I just traced the whole helix, you'd be able to see that this base is now appropriately positioned relative to the rest of the helix. So if you're tracing and you need to keep clicking on base, manually adjust, and adjusting chi by about 90 degrees, it's a good sign you're tracing in the wrong direction. Just a little trick if anybody winds up building something, you don't want to wind up tracing in the wrong direction. Delete trace. The other thing you can do with RCrane, I'm going to pull up the published structure again. So this is a molecule. I didn't build this with RCrane, but if, say, I just had a molecule that I just finished running refinement on, or I just finished running through mole probity, and there's a section of the molecule that doesn't seem to match the density, or that mole probity has told me that I have sugar pucker errors or steric clashes, I can use the rotamerize existing structure feature. So this works just like real space refinement or regularizement within Coot. Just pick the first suite that you want to rotamerize and the second suite that you want to rotamerize. And you'll get the RCrane window popping up again. And now it's going to rebuild that portion of the structure. So this is really useful if as I said before, if mole probity has told you that something has a wrong sugar pucker, it's typically very difficult to try to go in and correct that manually. But here, RCrane should take care of all of those errors and build a proper backbone structure for you. This will take a minute, but once it finishes, you'll get the exact same review suite window that we saw before. It'll tell you what conformers it built in. It'll give you a chance to try alternate conformers and flag any suites for you that it had problems building, indicating that either you want to try an alternate conformer in those cases, or maybe there's something wrong with the base or phosphate positioning. Let me jump back over the PowerPoint slides. I think that's about all I had. Yeah, that's pretty much the main features of RCrane. I'm still working on development of it, so I'd love to hear feedback, either bugs that people are having or more hopefully suggestions for new features that people would like to see. I have a couple of things planned that I'm hoping I'll get released soon. And Piotr mentioned there's a PNAS paper that describes the methodology behind this plugin. I'm working on another paper now that will describe more the plugin itself and some of the improvements in the methodology that we made since that original publication. Yeah, but I'll open it up for questions while this finishes rotamerizing.
Okay, so a couple more questions from the audience. People were asking about the alternative conformations. If it's something that you could accommodate. So alternate location indicators.
Right.
Yeah.
Right now, Coot can't. RCrane can't. If you try to rotamerize something with an alternative conformer, alternate conformation in there, RCrane will give you an error message. If you try to build one, you'd probably have to, I guess, trace it twice and then manually tweak things so that one is an alternate conformation for the other. That's something I can work on, but at least right now, unfortunately, no is the answer.
Okay. And another question was, can you changing directions of model building? Is it something that it's you're building 3 to 5 versus 5 to 3? Can you keep changing the direction as you're building the?
So right now, it only allows you to do a switch while you're building the first nucleotide. Part of the problem with doing a switch later is it's going to try to reposition all the bases, and so there's at least no easy way with an RCrane to go back and sort of fix it if it guesses wrong for how to reposition those bases. So right now, if you realize 3 nucleotides in that you are tracing in the wrong direction, you have to go back 2 nucleotides and then click the switch button and then retrace the other 3.
Mm-hmm. Okay. And this Ramachandran plot you showed earlier on, is it something that is not available right now within Coot, right?
No, so you can't do this within Coot. You can do this within Amigos 2. So I'm almost positive that's also available through SBGrid. So that's a Java application where you can load in an existing crystal structure. I've been told that it is available. You can load in an existing crystal structure, and it'll generate a Ramachandran plot for you. You can also use it to search for motifs. So there's certain signatures within the eta theta plot that you can use to find motifs. So there's a handful of features in there. Yeah, and should be available on SBGrid. So I think if you just type in Amigos 2 from an SBGrid command line, you should get that up and running, and then you can load in crystal structures.
Okay.
And do searches.
Okay. Any other questions from the audience?
I should say the rotamerization is finally finished. Again, really old laptop.
Okay.
But yeah, as you can see, it gives you pretty much the exact same window. Now it's telling you, just rotamerized suite number 368 and 369. Both of these look good, so they're both colored in white. And if you wanted to, you could select alternate conformers. You can also, I should point out, the original coordinates before we rotamerized are now shown in light yellow. The regular Coot coloring is the new coordinates that are built in. If you want, you can turn off the old coordinates to make the new coordinates a little bit easier to see. You can see it didn't really change things too much because this section of the structure is pretty good. But if you had some horrendous steric clashes in the backbone, or if you had some sugar pucker errors, they would have been corrected.
Okay. Again, if you guys have any questions, you can use the chat window in the events control panel to type it in right now. But if there is no further questions, thank you again for coming here today. And
no problem.
If you can put the last slide maybe
sure.
from the presentation. Again, the next seminar, Monday, December 12th at 4 o'clock. Jeff Head from the Lawrence Berkeley lab will talk about Phoenix. And thank you everybody for participation. Thank you for coming, and have a good weekend. Bye.